Hello. In this and the next few lectures, I'll be discussing what is known as alternating current. Some time back, we had talked about direct current circuits, and I would like to point out that in our day-to-day use, it is the alternating current which is uh, more prevalent than direct currents, and we will be discussing the various properties that go with it. But before we do that, let me remind you of what you have done earlier on Faraday's law. In our discussion of Faraday's law of electromagnetic induction, we had seen that if we have a situation where the magnetic flux changes with time, then an EMF is produced. The EMF relationship is given by the mathematical statement of Faraday's law, which says EMF is equal to minus n d phi by dt, where phi is the flux through each turn and n is the number of turns. If you recall, our definition of flux was integral of B dot ds over a surface. The formula is written usually with a minus sign, and that is because this is a reminder of what is known as Lenge's law. The Lenge's law talks about the direction of current induced in the circuit. So according to Lenge's law, now the direction of such induced current is always such that the magnetic field that such a current produces opposes the change that produced it. In other words, it tends to negate whatever change was being sought by the agency producing this current. Let's push this idea a little further. Supposing we have a rotating coil in a uniform magnetic field. So I will just give you a schematic diagram. So I have a coil which is rotating in a constant magnetic field. So this is the rotating coil. And let's suppose this is the direction of the magnetic field, which is uniform. And the coil, of course, moves around this axle. And suppose the direction of B makes an angle theta with the perpendicular to the plane of the coil. So let me represent it like this. So supposing this is the direction of the magnetic field, and this is a section view. So this angle is theta. So this is the way it's rotating. So therefore what happens is this, that the flux produced is, remember this is B dot A, that is B dot ds. So it is B times A times cosine of theta, which is of course a function of t, and that's equal to BA cos omega t, because the coil is rotating with a uniform angular speed omega. So therefore the EMF generated by it, according to Faraday's law, is N d phi by dt, which is equal to NBA omega sin omega, where N is the number of turns in that coil. Now this I can write as E0 sin omega. So since you notice that this EMF is changing sinusoidally, so therefore this will produce a potential difference which also changes sinusoidally. So let me say that the potential, the voltage V, is given by an expression like Vm sin omega t. Now suppose I am to plot this voltage against time. So this is a representative diagram in the sense that when I say t equal to 0, it doesn't mean that is the instant when the voltage was switched on, but any particular time you can take it as time t equal to 0 and proceed for one cycle. So supposing at my time t equal to 0, this is axis is time, my voltage happens to be 0, and then I go through one cycle. So this magnitude, the maximum magnitude of it, so this is my voltage V as a function of time, and this is Vm, that's the maximum voltage. So in this picture, what I have done is to say V equal to 0 at time t equal to 0. Now the voltage returns to the same value. So this is time t equal to 0 after a time capital T, passing through a full cycle, and this t, after which the voltage at any point in the circuit returns to the value that it had